Okay, let's get started. So if you haven't turned in your homework 2, make sure to do so. I think there's still a homework 1 that's been graded and hasn't been picked up, so if you're that person, please pick it up. Any questions since last time? Because the National Weather Service hasn't used covering arrays. No, I'm kidding. I'm kidding.
That was probably the most clever answer.
If you knew the answer to that question, you probably would be someone very famous. If you happen to know why it's snowing already, because then you can predict the weather patterns.
I'll chase that back.
Oh, all right. So on Slack, I posted the dates of the papers as well as who was assigned to each of them. So for those who never told me what day they wanted to do a paper, I just randomly assigned you a day. Okay. So those are set. The 2 people, I forget who, make sure to really read the paper for next week because you're obviously going to be presenting it next week. Okay? And what I would suggest for people who are assigned the same day, talk together so that you can figure out how you want to manage discussing the paper. Is one person going to talk about a specific section, or is one person just going to talk about, say, the mathematics behind it, and one person does the results, or however you want to break it up? Yeah.
For the paper, is it more like we're leading a class discussion, or we're like just going to be talking for an hour?
It's more of leading the class discussion. So I absolutely expect participation from everyone else who's not presenting the paper that day. So like asking questions for clarification, or what they think the author should have done, or what they think they have done well, like participating in addition to what the presenters are doing. But yeah, it's a leading of class discussion mostly. So I'll actually be sitting with you guys in the audience, and I'll be an active participant with you. And hopefully I'll be able to read the paper. Yeah, and hopefully I will, because I have a paper deadline tonight. So hopefully I make that. Okay, yeah, any questions about the paper presentation type things? So yeah, make sure to read that ATEACH paper by Friday next week. Okay, so we were talking about exact methods, right? So exact methods are you just plug in the parameters to some algorithm, and the algorithm spits out the optimal size covering array, either the size or the actual array itself. So we first talked about, let's just try every possible array, and that's obviously what you could do, but it's just really inefficient to do it that way. Then we talked about integer programming, which it isn't as used anymore as it used to be, primarily because other methods, which is actually one we're going to talk about later today, have gotten a lot faster compared to integer programming. But it may be worth looking into this because I don't know how much better the solvers have gotten here. It might be worth looking into. Then we ended on this graph coloring problem. So the graph coloring problem is we have a graph and we want to color the vertices properly. And by that we mean that if 2 vertices are connected via an edge, they do not have the same color. So like in this Peterson graph, for example, it'd be wrong of me to color this rightmost vertex blue because it's connected to a blue vertex. So you may think, well, we can just try every possible coloring here, but that's pretty slow to do because first of all, you don't know the number of colors that are sufficient. And even if you do know the number of colors, well, if we have n vertices and let's just say L colors, so yeah, let's just do this as an exercise. So let's just say we have L colors available and we have n vertices. So what are the number of possible assignments of colors, not necessarily proper, that could be done with this graph? Yeah.
You can have n colors.
No. Let's just say I have L colors.
Oh.
I've fixed you to L colors. So how many possible assignments of colors to vertices are possible? Well, each of the vertices can have any one of the L colors. Yeah, so how many in total? I think it's the other way. Yeah, L to the n, because the first one gets L possibilities, the second one gets L possibilities, etc. Yeah, so it'd be, if we wanted to do this exhaustively, then we would have to do something like L to the n assignments, which is obviously huge. So there have been quite a few algorithms that try to make this faster, but how many of you know what NP-complete is or have heard of it? So for those who don't know, NP-complete is just a way of looking at a problem and showing that we believe the problem to be hard. For our purposes, what that means is that there's no known polynomial time algorithm for graph coloring. If you happen to find a polynomial time algorithm, please let people know, or show that it doesn't exist, because you'll become famous overnight if you do. So we'll just have to go off the assumption that there's just no polynomial time algorithm. So there are some there are some fast algorithms for the graph coloring problem, but don't guarantee to give the optimal size coloring. So I'm using this in the paper I'm doing here. So the one that is actually pretty easy to understand is something called largest first coloring. So this might actually be interesting to look at in a project. So the idea here is you pick a vertex with really, really high degree. So the number of edges is very large with it, and you assign it a color if possible. So let's just say that we have every vertex. Actually, let's just do it this way. So let's just say we have this K4 graph right here. I'm going to copy it over here. And what we're going to do is we have a current library of one color. So we only have one color available right now, and then we'll eventually add colors. So the idea here is pick any vertex with the highest possible degree that you haven't picked yet. Well, we haven't picked any of the vertices, so does it matter which one I pick? No, they all have degree what in this graph? The number of edges. Yeah, 3. Because there are 4 vertices, each one is connected to everyone else, so degree 3. So let's just pick this top left vertex and assign it the color red. Then what we're going to do is pick a vertex that we haven't picked yet that has the highest degree that we haven't picked. Well, they all have degree 3 still, so it doesn't matter which one we pick. So let's just pick the top right one. So we'll try to assign it the color, one of the colors that in our library. So I'm going to have a library of colors right here, and so it's going to be a list of colors, and the first one is red. So that's our current list of colors. Then for the top right vertex, we try to assign it the first color in our list if we can. Well, can we assign it red, the top right vertex, to get a proper coloring? No, because it's connected to a vertex which is red, and that would have the endpoints of an edge having the same color. So what we do is we extend the list by 1. Let's just say I'm going to put blue into the list. And then now we'll assign that vertex blue color. And then we repeat with the next vertex. Let's say the bottom left one. Then what we'll try to do is try to assign it the color red. If it's not possible, try the color blue. If it's not possible, add a new color and assign it. So we can see easily that we can't assign it red or blue, so we have to add a new color to our list and assign the color to that vertex. And then if we carry through again, we're going to have to create a new color. Let's just say purple for the 4th vertex. And then this will produce some coloring, some proper coloring of the graph, because at each point you will assign a color to a vertex if it's possible. And if it's not possible, you add a color, but that can't clash with any of its neighbors. So therefore, you will get a proper coloring, but not necessarily the optimal one. And this is much faster because you're only working with one vertex at a time and just observing the neighbors of that vertex. So it's linear in the size of the graph. So this is actually a very, very, very fast algorithm. But it's just, it's not optimal. Okay, any questions on that one? So it might be worth looking into the formulation of the graph that we're going to talk about and applying the largest first algorithm to it versus what is the actual minimum number of colors needed. So like to see what the discrepancy is, if there is any. Okay, so why would we even talk about graph coloring here? So the way you think about this is the graph coloring problem says if we have an edge between two vertices, that means that we have some kind of restriction or constraint between the two vertices. They can't be the same in some sense. So if we, for example, look at the Peterson graph, the one in the center. So we can think of all of the red vertices as the same, so because they're assigned all the same color. So you can think of this as we are partitioning all of the vertices into equivalence classes, and two vertices from different classes can't have an edge between them. Because if there's a sorry. Two vertices within a class can't have an edge between them. My mistake. So what would we want to do here? So if we can find a way to look at different interactions in a covering array and say, if I have an interaction here and an interaction here, and I form an edge between them, then they can't be the same, just like with the colors in the graph. And why would we want to do that? Well, if two interactions can't appear in the same row, then they need to have a constraint between them because they can't appear in the same row. So let's just look at an example of this. So let's just say that we have two interactions. So let's just call them I1 and I2. So, and these are interactions, of course. So let's just look at, say, I1 columns. The columns of I1 are, let's just say, 0 and 2. So I guess we're looking at a strength 2 covering array. And then the values are, just as an example, 0 and 1. So we want interaction 1 to appear, which means that in columns 0 and 2, we're going to see the combination 0, 1 somewhere. If we look, let's just say as an example for the second interaction, that we have columns 2 and 3 and values, let's just say 0 and 1 again. Then that says in columns 2 and 3, we want to see a 0, 1 appear. So just to visualize what that even looks like. So let's just have columns 0, 1, 2, 3. So here are the columns. So interaction 1 says that in 0, 2 somewhere, we should see a 0, 1. That's what we want to see at some point. And for interaction 2, it says in columns 2 and 3, we want to see 0 and 1 in that order somewhere. So let's say maybe somewhere else, we see a 0, 1. Okay? In that order, crucially. So let me ask you a question. Can these two interactions appear in the same row? So think about it. Look at at column 2. The first interaction must have a 1 in that column, and the second interaction must have a 0 in that column. Can those two interactions appear in the same row? No, because if they did, that means that in that row, in column 2, we must have a 0 and a 1, which is impossible. So for that reason, we're going to put an edge between these two interactions. So in the graph, we'll have a vertex corresponding to I1, and it'll have an edge with vertex I2. Now, I don't really care which row those two appear in. It doesn't matter to me. What matters is that they can't appear in the same row. That's what's crucial here. Okay, does that make sense? Yeah.
So if we're making this general and the interaction is something like 0, 0, and 1 identical rows, or sorry, two different sets of columns, would you still care that they aren't in the same row?
Good question. Let's actually do an example of that. I think that would you want to do an example of where you would want, where you wouldn't want an edge? I think that might be a good idea. So let's just modify our existing example. Okay. Try to copy this all at once. So let's copy it down here. And now I'm going to make a change. I'm going to make the second interaction be 1 and 1. But everything else is identical. So that they share column 2, but now could they appear in the same row? Yeah, they could appear in the same row. I don't really care if they do appear in different rows. I don't care about that. I just care that whether or not they can't appear in the same row. Because for graph coloring, you're only interested in constraining two vertices. It could be that two vertices that are not connected get different colors. That's totally possible. And in fact, the graph here, say this vertex and that vertex, they're not connected, but still get different colors. So I'm not really caring about that. It's just whether they can't appear in the same row. Let's do another example. So now I'm going to modify the columns of the second interaction to be 3 and 4. And still leave the values at 1, 1, although it won't matter here. So should we form an edge between these two? Well, let's actually try to visualize it. So we have columns 0, 1, 2, 3, 4. So the first interaction, we want to eventually see 0, 1 in those two columns. And for the second interaction, we want to eventually see 1 and 1 in columns 3 and 4. So could these two appear in the same row, possibly? Yeah, and the reason is there's no columns in common. because there's no rows, columns in common, it doesn't matter what the values are in there. So the only reason you would ever form an edge, which I have on the slide here, the only reason you would want to form an edge is they share a column and they disagree in the shared columns. So if they overlap in 2 columns, then they must disagree in at least one of the 2 positions. Okay? Another example would be, let's copy it again. And I can give you code if you want to actually form the graph directly. That might be interesting for our project. If we have, let's just say, the 2 interactions having identical columns, then will we form an edge? So remember, we're always looking at 2 different interactions. They have the same 2 columns. Will they have the same 2 values though? No, they won't. So in fact, well, they share columns and they disagree in at least one of them. So you would always form an edge. So let's actually just write these down. So for the second example we did, that was no edge. The third one was also no edge, and this one is form an edge. So to recap, the vertices of the graph are every possible interaction, and we form an edge if the interactions are incompatible with each other. And by that we mean if they overlap in at least one column, and among the overlap columns, they disagree in at least one position. And what are the colors here? Well, the colors will be which rows of the covering array are there. So if there's an edge between them, then they get different colors, meaning they appear in different rows. So if you have an exact algorithm for graph coloring, you can find the minimum size covering array just by enumerating what the colors are. And in fact, what you can do is, if you have a coloring for this graph, just extract the interaction out of the vertex, figure out its color, and now you know what row it's in. So just put it in that row. So you can actually get the array back, which is really nice. Any questions on that? So there's actually one more exact method that's not in the slides, but I'm going to go over, and I'm going to do a little code example here, which is why this isn't full screen.
So does this prove that minimum covering array is NP?
And is NP complete? That is a very loaded question, and I'm going to not talk about it because there's a really important subtlety there. In fact, it's an open problem whether it's NP complete. And the main reason is, what is the representation? So the graph is the representation. The size of the graph, NP completeness is measured in the size of the input, which is the graph in this case. For covering arrays, what's the input? Do you get the array, or do you get the numbers n, t, k, v? Well, if you get the numbers, then the array is already exponential in the size of the input. So it doesn't really make sense to talk about like a polynomial time algorithm because there can't even exist one if you have that type of input. So there's a lot of subtlety there. Yeah.
So what kind of input then would make an algorithm for it, not exponential?
So this is probably going to bore everyone, but the most inputs when you have an integer are in binary. So a way to avoid that is to put them in base 1, which is exponentially larger than the base 2 version. So that's a way to get around it. But in fact, it's still an open problem even for unary base 1. So yeah, there's a lot of subtlety there. If you're interested in that, feel free to look into it, but I don't think it's really that an interesting of a question. Okay, any questions otherwise about this? So I want to talk about one more exact algorithm, which I didn't have time because of my paper deadline to put into these slides, and that is called satisfiability. If you have seen NP completeness, there will be reoccurring nightmares as you see this word. So how many of you have ever seen the Cook-Levin theorem or shown that SAT is NP complete or something? So have you seen the proof of SAT is NP complete? Not formally, okay. You've been spared of it's a very, very involved proof. But so what is satisfiability? So can anyone tell me what the satisfiability problem is? Just at a high level, yeah.
Basically, you want if you're just given some true formula,
Yeah.
and you want to find some combination of true price values that makes the set true.
Yeah, exactly. So we have a Boolean formula. So so let's call it F, and let's just say it takes Boolean variables x1 through xn, and it outputs false or true, 0 or 1, it doesn't matter. And we want to find an assignment to the xi such that the output is 1. Okay? How many of you have not heard what conjunctive normal form is, or CNF? So everyone's heard of it? Okay. Yeah, so what we would want is to have a formula in conjunctive, if I can spell it, conjunctive normal form, or CNF. So there's a lot of ways that you can formulate the covering array problem in terms of a Boolean formula like this. So one way that I've looked into is to do two things. So the formula that we'll build has two parts. So the first part is each entry has exactly one value, and the second condition is every interaction appears. Okay. It's actually an open problem if there exists a CNF formulation for the covering array problem. If you can find one, please let me know. A CNF formulation, I should say a direct formulation, because you can convert any Boolean formula into CNF, so it's not really right for me to say there's no formulation for the CA problem. And it's unlikely that one exists, but maybe there does. So I'm actually going to switch gears here. And you won't see this on the video, unfortunately, but you can see it here. And I'll share all of this code with you. So this is actually some code that I've used in a lot of my research. And basically what it is it formulates the covering array problem into a Boolean formula that's not in conjunctive normal form. And then I feed it to a solver that works with formulas that are not in conjunctive normal form. They can convert it into CNF and then solve the CNF formula using a known SAT solver. So let me actually go through this with you. So up here, I have the four values, n, t, k, e, and v, the ones we know and love. And this lambda right here is the higher index covering array. The usual definition is 1, so we're going to actually just use 1 here when I do these examples. But you can feed in other values if you want. Okay, so I break up the formula. It looks complicated, I know, but I break it up into 4 pieces. So the first one, you can ignore all the details of it, is basically exactly 1. That little formula means that every single entry has exactly 1 value. So the encoding that we are using here, maybe I will use this a little bit. So the encoding for the variables is of the form xijl, kind of like the integer programming formulation that we did before. So this says in row I, column j, the value L is placed. So if that variable is true, then L is in that location in row I, column j, and if it's false, it's not there. So because there's no inherent relation between, you have a question? Okay. If there's no inherent relation between 2 variables unless we put a clause in or some type of constraint between the variables. So what this says is this first part right here is saying there's at least 1 value that's set to true. So among all the possible choices of L, there's at least 1 of them that's set to true, because there must be some entry in that position. And this really, oh god, for this second part of it is saying that 2 variables can't be set to true. So it can't be that, say, x000 and x same entry but a 1 cannot be both be true. And so that's what I enforce here. So if they're both true, then I have to insert 2 values in 1 position, but that's obviously impossible. So yeah, so this little formula is just saying that there's exactly 1 value in each position. This really long thing is just saying that every interaction appears. So the first for loop right here is for the choice of t columns. I just use itertools combinations. If you know Python, this is a really nice function for covering array stuff because it can do all the work for you. So for every choice of t columns, for every choice of t values, then basically this part, I'm just going to skim over it, is just saying the interaction appears at least lambda times. You can think of it as just the interaction appears. That's it. And that's all this does. And in fact, if we just have this formula and the all covered somewhere formula, then we're already done. So in fact, I can comment these out, and then let's just see if I can do this. And then we can actually run it ourselves. So what I do is this last bit right here is saying the exactly 1 formula has to be true and every interaction appears also must be true. So both of them have to simultaneously be satisfied. So what I'm going to do here is, you see this limbool thing at the top? So limbool is a tool that, the only one that I know of, that can take a formula in not in conjunctive normal form and then solve it. Pretty much every SAT solver in existence works with a formula in CNF already. There's a specific format that they use. But if we run this, let me give a smaller example. So let's just say that we're just doing the really simple example with strength 2 and 2 values and 2 columns. So if we have 2 columns, so 0 and 1, and let's just say the strength is 2 with 2 values, how many rows are we going to need? Well, there are only 2 columns, so what are the interactions that must appear? 0, 0, 0, 1, 1, 0, 1, 1. Do we need any more? No. So, in fact, what we should see is 0, 0, 0, 1, 1, 0, 1, 1. So let's actually run this right here, and I'll give you the code for this. So what I'm asking here is, I'm going to make a formula that works with 4 rows, strength 2, 2 columns, and 2 values. But I also, for purposes of this program, I have to put the number of times that each interaction appears, which I only need 1 here, because every interaction in this array appears exactly once. So if I run this, it gives you a bunch of stuff, because I have it on verbose mode. You can turn that off. But what appears is right here, which says that the encoding here for row 0, column 0, the value 0 is false, is 0. So that means in the first row, so first row, first column, maybe let's actually look at what was produced. So in the first row, first column, we have a 1, yeah. Oh, sorry. I need to get better at this. Yeah, so in the produced array, then we have the variable 0, 0, 1 being true, which means in the first row, first column, we have a 1. So then in the second column, we see the value 0 is being true, so then a 0 is there. Then in the second row, first column, the value 1 is true, and then we better see a 1, and we do. Then in the third row, we have a 0, and then a 0, I think. And then in the last one, we get a 0 and a 1. So it's not the same array, it's equivalent, because we can just rearrange the rows as we need to. What if I tried this same thing, but with 3 rows? What should the formula say, the solver say? It's not possible to satisfy this. So if we run this and we look up, it says unsatisfiable. So there's no way to satisfy the variables here such that the formula is true. There's no way to satisfy it. So we can feed in larger choices such as 7, 2, 15, 2. Does this one seem a little familiar? And then that one's true. So what you could do, and this is what I've done in related work, is you can just parse this directly, just parse it, and then you can actually make the array from it. So if it's 1, then you put it into that position, that value into that position. Then if I try 6 rows, then it's going to go for a while, and I'm actually not sure how long this will take. But it will eventually report unsatisfiable. So what problem do you think is much harder to do? To show that there is a satisfying assignment, or show that no assignment can satisfy it? Which one do you think is a harder problem, potentially? Either give one example of a satisfying assignment, or show that none of them exist. Show that none of them exist is harder, right? Because you would have to demonstrate in some way that all 2 to the n possible assignments cannot possibly satisfy the formula. Yeah, this is. Yeah. So this solver, Lingling, is what is called a look-ahead solver. And I'm not sure about the details, but the basic idea is it tries to, let's just say we want to look at a variable that we haven't shown it must be set to true yet, and let's just assign it temporarily to true. Then if we get some kind of contradiction down the line, then this variable must be false, and then we try again. So it looks ahead, and if anyone happens to know or can tell me that that's wrong. Anyone know? Okay. So therefore I'm right. Yeah. Yeah, so that's the basic idea. And I have it on verbose mode. So these conflicts are basically how far is it looking ahead to try to find a contradiction, and it couldn't find one yet. So if you actually notice at the top, so the number of variables after some kind of simplification has 5,000 variables and 16,000 clauses. So, and then it goes down to 900, so it was able to remove some of the redundancy. So we can actually speed this up substantially, so I'm going to stop it. So what could we do to actually simplify this? So one technique that is really worth looking into, and I don't think anyone is, and this might actually be very revolutionary if you can show that this really works, is something called symmetry breaking. So this might be a very worthwhile project. So what in the world is oh, you guys need to tell me this. Yeah, symmetry breaking. Yeah. So what is this? So if you just think about the formula that we've developed here, it just says every interaction appears somewhere, right? Every interaction appears somewhere, and there's we don't care where the rows are. We don't care what values are assigned to one position. We don't care about the column order. We don't care about any of that. So remember when we were talking about like the different operations on covering arrays, where we can like say swap two rows and it doesn't change anything, or we swap two columns and it does the same thing. So those are symmetries in the formula. So if I swap two columns and look at the resulting assignment, then those two assignments will have the same answer. Either it satisfies the formula or it doesn't. So what symmetry breaking is we're going to do something to the formula that we're going to fix some of the variables to be true, that without loss of generality. We're going to assign them to be true. And so how in the world are we going to do that? So it's best to look at an example. So let's just say we have 15 columns. So let's just say 0, 1, 2, 3, 4, etc. up to 14. So here are our columns. And let's just say our strength is 2 and the number of values is 2 also. So here's what symmetry breaking is doing. Can we, without loss of generality, say that one row is all zeros? Yeah, because we can rearrange the values within each column to have a row of all zeros. We standardize the array. So that's one symmetry breaking idea, is just to set the entire first row to all zeros. The formula before allows for that as a satisfying assignment, potentially, but we're forcing it to be so that the solver can make decisions based off now there's not as much symmetry, now we have a choice as to what to do. Because with symmetry, it could be that we can go down this route or this other route or this other route. But if we fix some of the entries, now it has fewer options and thus runs a lot faster. What is another symmetry that we can do? So this one's a little less easy to see. So remember, we can always rearrange the rows however we want. So what we can do is look at the first two columns. What could we do? We can assign the first 4 rows to be 0, 0, 0, 1, 1, 0, 1, 1. All we cared about in the original formula was everything appears somewhere. But now we're forcing that the first two columns where they cover those interactions are at the top. So again, we're forcing some of the variables to be true. So by doing this, we are setting more of the array to be true, and now the formula is smaller and is not symmetry. There's not as much symmetry anymore. So now we can actually have the solver make better decisions. So that's what these last two things that I commented out do. So the first T covered little formula is just saying that the first T columns have those interactions appear right at the top. And we don't care what appears after it, we just care about the first T columns. Everything is covered in the first V to the T rows. And this first V column, little formula, is just setting the first row to be all zeros. That's all it does. And then if we restore what I had here, now I'm going to include those two little formulas together and AND them all together because I want all of them to be true. So if I run the 7 example that we did before, it runs at about the same amount of time. If we do the 6, now notice that the formula now has only about half as many variables and was able to show that it's unsatisfiable. So in fact, symmetry breaking is really, really crucial to solving really big instances like this. One more that is actually worth looking into that I haven't looked into very much and has gotten a huge amount of press lately is something called Cuban Conquer. I remembered. Cuban Conquer. So, how many of you have, a few years ago, there was a paper that came out that got a huge amount of press coverage. How many of you have heard of the Pythagorean triples problem? Okay, so it was this famous paper that made this giant formula where they had, they wanted to color the integers 1 through some number such that if we have a Pythagorean triple like 3, 4, 5 or 5, 12, 13 or something, that those don't have all the same color. And what we can do is we can just look at bigger and bigger sets of integers, 1 up to n, and make n bigger, and just see if there's a point at which the formula becomes unsatisfiable. And what they were able to show via this method was that it is true. And what it does is it basically does a depth-first search of the satisfying assignments in some way, which is actually what the solver does, but it does something interesting. So let's just say that we have a computation tree like this. So like for the first variable, we can either make it true or we can make it false. Make the second variable true or false, etc., all the way down. So what the Ling-a-Ling or most SAT solvers do is they try to explore this tree all the way to the bottom efficiently. What the Cuban Conquer algorithm says is, let's just say that the bottom vertices are down here. What it does is it tries to stop at a reasonable point up here. So at this point, it'll try to stop at some point that it thinks is good for some definition of good. And why would it want to do that is by stopping early, we have a fewer number of cases to check, and what the solver can do is work with each of those different cases independently and in parallel. So like this red blob might be the set of variables that are not set to true or false yet, but what you do is you go down the tree, set the variables to true or false as you go, and then deal with the rest of the formula all at once, kind of like the symmetry breaking argument that we just did. And then what it does is it has a bunch of these instances that each of them is very efficient to solve, but there are many of them. But we can parallelize it and make it a lot faster. And what they were able to do in many combinatorial problems is speed them up substantially. And there hasn't been any work on these applied to covering arrays or any related thing. I actually did try it once, and just from just rudimentary analysis, it just took too long to make all of these cubes. The cubes are each of the instances. And so it may be worth looking into. So I'll see you all on Monday.